Today, I'll be talking about our work, Fast Adapting V2X Networks, a dynamic context clustering multi-arm bandits. We will call it DCC for short from now on. For today's content, I will have a quick background overview, followed by the limitations of the related work. Then propose our DCC framework, and then show the simulated results, followed by conclusion and shed a light on the future work. V2X communication in the autonomous driving requires GBP level data rates and low latency to support the real-time traffic management and safety-critical applications, which goes far beyond what conventional sub-6 GHz systems can support. The millimeter wave is a natural candidate with its abundant spectrum, but it has a critical weakness that the signal is easily being blocked by obstacles such as buildings and vehicles. This brings us to a user association problem that each vehicle must continuously decide which base station is the best to connect to under a scenario of ever-changing channel brought by the vehicle's movement. To make things worse, obtaining accurate channel state information in conventional association scheme in real time is costly. So how do we approach this? We use the multi-arm bandit framework, a classical online learning method that learns through real-time interaction with no offline training required. In our setting, each base station is an arm, and the vehicle acts as an agent who learns which base station is the best to connect to by continuously pulling the arms and then observing the rewards. The MAB fits naturally here. It balances the exploration and exploitation, it runs with minimal computation, and it also enables a millisecond level decisions. However, the existing MAB-based approaches have several key limitations. For the traditional MAB, it assumes stationary rewards, which clearly fails in the millimeter wave vehicular networks where the blockage and the mobility cause constant channel fluctuation. And for the context MAB, it incorporates site information as a context to handle the non-stationary environment. But it usually partitions the context space into fixed hypercubes, like this. This creates a fundamental trade-off. If we define it too fine, then the hypercube space explodes at the network scale. If we define it too coarse, it will hardly capture the channel dynamics within each hypercube. And finally, the single agent MAB wastes the natural opportunities offering here, where the vehicles have high chance to share the same trajectory which undergoes similar channel changes. So the learned knowledge should be shared across agents. And this has bring us to our core question. How do we make a fast, channel state information-free user association decisions in a large-scale urban millimeter wave V2X networks? So let's consider this kind of scenario, that the vehicles are moving through an urban environment, and each vehicle will decide in real time which base station is the best to connect to. This process will be that each vehicle senses its current position as a context and then select the base station based on the context and the past experience learned. And then they will observe a resulting communication rate as a reward from the base stations. And then a macro base station coordinates the learning process across all vehicles. Our ultimate goal is to maximize the network-wide communication rate. So under this scenario, we propose our DCC SMAP framework. The architecture operates through three interconnected stages. The first stage is the distributed learning, as shown in the middle part in this figure. During this stage, each vehicle independently observes its position as context and selects a sub-base station which offers millimeter wave service using a local bandit policy, either upper confidence bound or Thompson sampling. The current position and observed reward will be stored as a context reward pairs, which are periodically uploaded to the macro base station over a sub-6 GHz link. The second stage is the center clustering. The macro base station aggregates all uploaded samples and executes our dynamic hierarchical clustering algorithm to identify similar context reward patterns across all vehicles. And the output is a set of clusters, each representing a generalized mapping between the spatial region and the expected reward vectors of the sub-base stations. And the third stage is the knowledge transfer. Vehicles query the macro base station under two conditions: when they first arrive in the network, or when their positions shift significantly beyond a threshold. And in both cases, the macro base station identifies the nearest cluster and then transfers that pre-learned knowledge within that cluster to the vehicle. For the new arrivals, this completely eliminates the co-star problem in the bandit exploration stage. And for the existing vehicles experiencing a context shift, this enables rapid adaptation rather than a restarting exploration under a new channel environment. Now let's go deeper into the clustering mechanism in the macro base station. The macro base station maintains a sample pool containing historical context reward pairs uploaded from all vehicles. We then apply KD tree-based hierarchical clustering algorithm to this sample pool. The key design is to evaluate the similarity jointly on two dimensions. First is the spatial distance between the vehicles and the similarity of the estimated reward vectors across all sub-base stations. A spatial distance threshold and a reward difference threshold are defined to allow aggregating samples that are close in both dimensions into the same cluster. Crucially, these clusters are dynamic. As more samples accumulated over time, clusters are merged, refined, and newly created to track shifts in the reward distribution caused by channel variations. And this means that the cluster count adapts organically to the network dynamics rather than being hard-coded as the previous context MAB. We built a high-fidelity simulation grounded in real-world data. The scenario is an urban area in Hachioji, Tokyo, with base stations locations drawn directly from the OpenCLID database, reflecting a real-world base station deployment. And the vehicular traffic follows a 3GPP standard via Sumo. And the millimeter wave channel is modeled using 3GPP CDL model with ray tracing. Now let's look at the convergence results. The x-axis is the learning time in steps, and the y-axis is the average regret, which measures how far our algorithm's association decisions are from the optimal choice. And the solid blue and green curves are the DCC using either UCB or Thompson sampling policy. And we can see that it converges stably from the very start, which means that the DCC allows vehicles to learn faster through dynamic context clustering and knowledge transfer. We also compare our method with the fixed context spacing partition context MAB and also the traditional MAB assuming stationary environment. We can see that the context MAB baseline fluctuates over time. And notice that the regret increase around the time steps of 30 might indicating some new vehicles hit the unexplored context hypercubes, and the bandit start to explore from scratch, which brings a large regret. And the standard MAB baseline just fails to converge completely because without the context awareness, it simply cannot track the non-stationary channel. So to conclude, the proposed DCC SMAB achieves nearly about 61% regret reduction than the fixed partition CMAB, and which reflecting a fundamental improvement in handling context space scale and also the non-stationality. Beyond convergence, we also evaluate the network throughput and the robustness of our algorithm. On the left-hand side, the DCC consistently achieves higher network throughput across all transmit power. We can also observe that the UCB policy outperforms the Thompson sampling policy here. which we attribute to the UCB's deterministic exploration strategy being better suited to the frequent vehicles' arrivals and departures in our setting. On the right-hand side, each box plot aggregates 40 independent trials with different base station deployment configurations within the same area. We can see that DCC achieves the lowest medium regret and also the narrowest variance spread, confirming robustness across all network topologies. While both baselines, in contrast, show high variance, which means strong sensitivity to the network topology. To conclude, we propose a dynamic context clustering semi-distributed multi-arm bandit algorithm for user association in urban millimeter wave V2X networks. The core idea is to cluster vehicle context dynamically and also enabling knowledge transfer that will achieve a faster network adapting ability without any CSI acquisition. And we are planning to analyze the signaling overhead and the scalability of the clustering procedure. And we are also planning to explore richer context representations such as velocity and heading of the vehicles. This is for the scenarios where the positions alone might not be sufficient. So thank you very much for your attention, and I hope you enjoyed this talk.